I wanted to talk about, I've been thinking a lot about LLM applications, building a lot of little demos, talking with people who are putting these things in production. And as I started to sort of like dig into the ideas that came up, the like concepts and patterns, I found myself going sort of like backwards in history. With this new technology wave, there's this belief that this is like brand new and it requires a complete rethink of the way that we do things, and that's not entirely wrong, but there's also been like a half-century of work in operations on handling these like opaque systems, complex systems, systems that we don't understand or are non-deterministic. In like diving into this past, delving, if you will, I feel like I've learned a lot that has helped me avoid mistakes with AIOps. So people are currently obsessed with the idea of evaluation. And one of the reasons why evaluation has become so important is because it supports this nascent practice of operationalizing LLMs and artificial intelligence. And its centrality is physical in this diagram from Hamel Hussein about the cycle of developing LLM applications. It's right there in the middle. Evaluation and curation of data is the most important and core part of this loop for developing AI applications. And we've already gotten some like sort of novel insights or specific insights from the last year and a half of building with LLMs. One key unintuitive point is that you want to actually simplify tasks for evals. Some of the power of large language models is that text comes in, text comes out, maybe multimodal data comes in, multimodal data comes out. And that's powerful and flexible, but it's like too complicated to write tests for. How do you know whether an answer is correct? So focusing the task itself, and especially the evaluation task, down to the simplest, distilling it down to the simplest case, like is this right or wrong? Is this feature present or absent? Rather than say, like provide feedback on this answer, has sped up people's evaluation pipelines and iteration cycles. Another one is that in this setting, you could basically trust no one. A lot of the software that is out there is very fresh and new and has not been tested. It's operating on these unstructured data types where they have trouble testing the stuff that they are doing. And on top of that, the failures that occur are generally silent. And so you will not know that you have accidentally been tokenizing your data incorrectly or differently in fine-tuning than in your inference. And so you have to adopt a very paranoid and defensive mindset. And then lastly, the maybe most important insight from the last year is the power and the limitations of synthetic data. So with synthetic data, we take data generated by one language model and we use it to train another. And one of the things that makes this particularly powerful is that it's a well-posed machine learning problem. You have a data generating process that you like completely control, as opposed to a data generating process that's out there in the world. And so you just need to mimic that data generation process. You need to mimic the behavior of an existing model. Takes all of the ML complexity out and becomes relatively simple. This synthetic data also kickstarts the data flywheel, the process by which we accumulate data, which allows us to make better models, which allows us to collect more data. The problem with that was always, well, where do I get the data at the beginning? And the answer was to steal it from the internet at scale. But now you can start with one of those models and get your data flywheel going. And then finally, the pattern that has generally worked well is actually not to go entirely from scratch, but to enrich the data that you are able to find. So to use language models to take data that's like customer behavior in your support chat and turn it into rich data that you can actually train a model on. So a lot of those insights are not entirely new to like AIOps or the use of foundational models. They come from MLOps. So there's an equivalent loop for MLOps that comes, in this case, from a paper by Frye, Shankar, Rolando Garcia, and others on operationalizing machine learning. As before, data collection and experimentation are at the core of this loop. This was also the loop that we put at the top of the page in the full stack deep learning course back in 2022 when we were teaching people how to go from research ML projects to actual products. This loop was at the core of it. And the MLOps, which roughly is like going from scratch rather than going from one of these existing pre-trained models, had its own insights. Number one, pipelines, not models. The system that produces models is the store of value, not the weights themselves. Will made a similar point in his talk. Despite that, actually fully automating that pipeline proved to be an elusive goal for MLOps. Like automating that entire pipeline that produces models so that all it needs is like the same kind of babysitting that any complex software system needs eluded basically all but the most sophisticated teams working at the largest scales. So Rohan Anil and others at Google wrote an incredible paper from the factory floor about how they fully automated essentially the pipeline for creating ad click-through rate prediction models. But unless you have the resources of people serving ads at Google, it will be very challenging to achieve that degree of automation. The final and most important insight from MLOps in particular was the importance of looking at the data. So this is a collection of very cracked ML researchers and engineers all saying, begging people to spend more time looking at the data, saying it's the most important thing they think about when hiring, saying that when they see leaders at ML organizations who they respect and admire, they find that they in fact are on the lines creating annotations and reading data. So make it part of your stand-up, make it part of your on-call. This is unintuitive for software engineers in a way that was surprising for me coming from machine learning, in that traditional software systems are essentially defined by their lack of interest in the semantic content of the bytes flowing through them. And so you don't actually need to look at the user data that much. You should be thinking about the code. You should be thinking about the structure of the application, and that will ensure correctness. But this is not the case with ML, and this is the sort of key insight from that era of operations. But MLOps did not invent the operationalization of software systems. MLOps is a component of the overall development operations of an organization. So DevOps has its own loop. Topologically, that's a loop, even though it looks like an infinity sign, where you close the gap between the development of applications and the release of applications. And that loop is closed by monitoring the data in order to decide what to do next. So there are a number of key insights from DevOps that you can port to your AIOps. Number one is that you want to automate everything that can be automated. You want to be able to move through this loop as fast as possible, so you need to get rid of all the slow steps, and machines are the best way to do that. But zero-click deploys also somewhat elude the DevOps in the same way that full automation of continual learning evaded MLOps. So you end up with one-click deploys where somebody has to sort of LGTM, has to choose to merge a PR in order to kick off an automated release, and a similar automation but with bounds is likely to pertain in AIOps for the foreseeable future. The bugbear of DevOps was difference between development and test environments and production environments. The same applies in ML. Make sure that the data you are developing on, the data you are training on, the data you are evaluating on resembles that production data as closely as possible. And lastly, perhaps most controversially, is the idea of testing in production. So testing in production, determining whether your system is working on the basis of what is happening to actual users, has turned out to be very powerful for DevOps. However, the thing that made it actually particularly powerful was not merely monitoring and being able to see what is happening in production, but a deeper level of knowledge of the system, which is observability, or its control theoretic dual controllability. So the idea is that you should be able to figure out from what you see in the production logs how to fix the system. No need to shell into it, no need to recreate it in a debugging environment. You can observe the traces and from that figure out how to fix it. That, because of the opaque nature of ML models as a giant soupy pile of floating point numbers, this is extremely difficult for ML. Recent advances in mechanistic interpretability are chipping away at that opaque facade, but that limits the efficacy of testing in production. But it's the only place to get good data, so you're kind of stuck with it. DevOps is itself derived from the lean, the various lean movements, maybe most prominently the lean startup movement. So folks talking about DevOps like Gene Kim, call back to this, Eric Ries in the Lean Startup focused again on this loop of iterative experimentation focused on measurement and data. There are a number of insights from Lean in general for AIOps. Number one, the minimum viable product. How can you avoid having to build the full thing? Can you do this with a human in the loop? Can you do this with traditional software? Can you use a button on a website instead of an LLM? Maybe the subtler key insight from Lean Startup is the idea of the 3 A's of good metrics. Good metrics should be accessible. Everybody who needs the information in that metric should be able to see it and maybe change it. So Langsmith, an LLM ops tool from LangChain, makes accessibility of metrics a very key component. It's interactive, easy to enrich. The good metrics should also be auditable. You should be able to discover how that metric was calculated. That's a strength of Weights and Bias's Weave product, which allows you to figure out which version of the code, which version of the prompt and model was involved. Actionable is kind of one of the missing pieces here. How do you actually make it possible to go from the information that you get in your observation and turn that into improvements? So there's an open hole here that many of these AIOps providers are working on filling. But Lean Startup maybe has this sort of association with Silicon Valley and with high tech, but it actually, the roots of this go all the way back to Toyota. So this is made very clear by Gene Kim and others in the Phoenix project, their novelization of DevOps, which is far more interesting than it sounds. It's also something that Eric Ries calls out in his introduction to the Lean Startup, that things were sort of confusing. He had these intuitions about how to build startups effectively, but it wasn't until he studied lean manufacturing and the Toyota production system that it all kind of clicked for him and resulted in the Lean Startup system. This is something people also wrote all the way back at the time about lean systems and their connection to Toyota. Sort of one of the sort of core things at the center of the Toyota production system is Kaizen, or the concept of continual improvement, and it is the very same loop that has connected all of these, operations disciplines. There's a bunch of key insights from this. A lot of them have already been sort of talked about in these other disciplines. The idea of Genshi Genbutsu, or real things, real places, has its equivalent in look at the data. You don't just operate in your boardroom talking, or in your Slack chat talking about what users need. See what they actually need from the real data. Make issues easy to see. These failures are silent. They should not be silent. Attempt to lift them up as high up in the stack as possible. But maybe the most important concept from the Toyota production system is the idea of the single-minute exchange of die. When you needed to switch over a machine from creating one part to another part, it could take up to hours to move heavy components from one machine to another to get a component from one end of the factory to the other end where it is now needed. And through simple techniques of just rearranging where objects were, Shigeo Shingo was able to take the die changeover time that changed which products the factory was producing down from 12 hours to under a minute. And this was what allowed them to become responsive to customer demand. So the overall goal with these operations disciplines has always been to achieve single-minute exchange of product in these various disciplines. And that is the primary goal we should have in our AI ops. So that's the primary lesson that I've learned from this, and I look forward to developing applications on this principle and building and using the tooling that supports that.